we are going to talk about functions and vector. And if time allows, we will start our discussion on matrix as well. So, well, why we study this? So, well, machine learning is some kind of a mixture between something called model and data. So it's a practice playing in between some models and data. And in order to represent some object, some kind of concept, some kind, well, anything. In computer science, we need data structure. And in order to build a right program, in order to create, well, supposedly proper program, well, one of the conditions, you need to have right data structure. So if you pick up wrong data structure for your program, well, that's the end of your program life cycle already. So well, if you choose a wrong data structure, your program cannot be really good. Well, given that data structure is really important and some kind of corresponding concept for machine learning, in order to represent the data properly, we need to know linear algebra. So linear algebra is a part of math, but still, well, specifically, we need linear algebra to represent data. So the outfit and the appearance and the outer shell is something called the edge function. So this is just some kind of outer shape of the model. And we will then move on to some stuff from linear algebra. And next week, I'm planning to cover some of the important concepts on calculus. And stats and probabilistics. And these are fulfilling the linkage between data and function. At the same time, these are useful tool to represent model. So these are well sort of rough idea why we study these. So let's get started. So functions, well, from the elementary school, we have drawn this kind of diagram. So you have input and output, and there is black box. So there is a function, and function is doing something, and function can be understood as your program. And in machine learning, we represent this, well, sometimes as a mapping, sometimes decision function, prediction function, or classifier, regressor, or whatever. There are a bunch of different names for this function in machine learning already. That means function is something we want to obtain at the end of the day. And x and y, these are input and output of your function. And we provide the data to fulfill those sort of role in this diagram. But given that, let's start from the easiest and simplest, but the most important form of the function, that is first order function. So first order function, nothing but where you have unknowns, and the degrees of the unknowns is just first order. So you have two constants, that means these are known, and you have unknowns. And this function is basically explaining the relationship between two unknowns. And the relationship can be explained in this way: ax plus b. A is constant, b is constant. In particular, a could be understood as a slope. So how much it is its length. And intercept, where this line is meeting with y-axis. So we have studied this from middle school, where it is called as 기울기 enjalpion in Korean. So this is simple, and basically this simple function is explaining the relationship between x and y. So once you have it, you can explain whatever given x, you can sort of map the right position for y. So here comes two examples. One is y, 2x plus 1. That looks like this. So this is the slope, and this is the y-intercept. And if you change the sign for those constant, so -2 and -1, where basically you are mirroring the graph against the y-axis. So the slope changes. And at the same time, you change the y-intercept. So this line meets the y-axis in this position. And in the previous example, you had only one unknown on the right-hand side. If you have more than one unknowns on the right-hand side, this is going to be something like this. So in this example, you have 3 unknowns. Out of these 3 unknowns, 2 are on the right-hand side, and 1 is on the left-hand side. So something, this is a convention. This is not something you have to, but something right-hand side is interpreted as input, and something on the left side interpreted as output. So again, this simple function is explaining the relationship between x1 and 2 and y. And we have 3 constants, a, b, c. So we can easily think of this shape of the function. So basically, you're defining a plane in some space. So out of this, we can get some generalized idea. So initially, we have 3 unknowns. That means we have 3 moving parts as an axis. And you have 2 unknowns. So we have 2-dimensional input, maybe input. And this defines where you will get a shape of 2-dimensional something that is a plane. Well, in the previous example, the input space was just 1-dimensional. So what you get at the end of the day was a line component. So depending on the dimensionality of the input, you're going to get some hyperplane input. Let's say the dimensionality of the input is d, then you will get d-dimensional hyperplane. So this is the general idea. And throughout the semester, we are going to find out this kind of a format a lot. So you will get in love with this first order form between set of input and set of output. So let's get familiar with it. And here comes second order function. So second order function, where the change is where you have unknowns, and the degree of those unknowns are second degree. So again, A, B, C are constant. And in particular, when A is positive, then the graph looks like this. So when your second order function looks like this, where this is called as a convex function, it looks like convex. And if A was a negative value, then your shape is upside down. And when your function looks like this is called as a concave function. One important point here, when you have a convex function, you have a single point of the value that makes the minimum in terms of y. Concave function is the opposite. So if you have a concave function, you have a maximum value. And here comes slightly different form of the same function. So where you can rearrange the function format, and where if you do something that we call as 소인수분해, then you can make some things in this format. Where something like this. Once you have the second order function in this format, where basically you can find out the value that makes the minimum in terms of x is better. And the intercept over here, so where the graph and this is hyperbolic and y-axis meets is gamma. And this decides the shape. So where how fat it is or how slim it is. So basically we are defining a hyperbolic function that goes around some point with a certain shape. So straightforward. And again, we are going to see more than one unknowns in the right-hand side. So in the previous example, this is the simplest form. We have only one unknown, but where we have to generalize it because our data has more than one variable. So in this example, you have two variables, x1 and x2, and that is getting started a little more complicated. So it is defining a hyperbolic on three-dimensional space. So x1 and x2 on the bottom, and the axis over here is defining y. So this is the second order function. And here comes some special functions. So unit step function is basically when the input value is smaller than 0, then it's basically 0. And input value is larger than or equal to 0, then it's going to be 1. So there is a big jump on this point. And the initial form of the neural network, where this was the initial activation function. So long time ago, people tried to represent the neurons and the communication between neurons mathematical way. And this was one of the initial form and initial activation function. One problem is in that context where there is a discontinuous point. So this is non-differentiable. That is one of the caveat. So later people, they try to change it, the activation function with different functions. So if you have any exposure to neural network, you have heard of this. So where functions like this. So all these are different names of function, and we will learn throughout the semester. And here's another special type of function that is exponential function. So exponential function is basically in this shape. So you have a known constant. Given that, depending on the input value, you're deciding the output, basically a to the x form. So if a is large, then where this exponent function grows faster. If a is smaller, then this exponent function is growing slower. And there is one important special case for this exponent function. So when your base is E is the Euler's number, well, in Korean, we have studied this as a 자연수, but I'm not sure 자연수 is correct, but well, you know the value. So E is equal to 2.718281828, blah, blah. And this defines natural exponent function. And this is quite useful because, well, this property, so at any point on this line, the slope of Ex is equals to the value of Ex. So at any given point on this Ex slope, Ex curve, where if you measure the slope, then the value of that point is the same as the slope. When x is 1, e to the 1 is e. When x is 0, e to the 0 is 1, and slope is 1, and something like that. And let's move on to the sigmoid function. So sigmoid function is, well, used a lot in neural network, and at the same time, a model that we are going to study named logistic regression, which is my favorite statistical model in entire machine learning mode. Sigmoid function is, well, one part of it again, and that looks like this. So we'll notate it using this sigma, and looks like E over 1 plus e to the minus x. And well, this exponent notation is sometimes confusing. So well, same notation could be something like this. So some people prefer this kind of notation. Well, there are good property of this function. So the function is bounded in between two certain values, so 0 and 1. So it never goes beyond 1, never goes below 0. And using this property, we are going to use this function to represent the probability. So probabilities is where some numerical expression representing where some event happen out of 100 or something like that. And we often represent this probability value, some value between 0 and 1. And since the output of the sigmoid function is defined in between the domain of 0 and 1, we use this function to represent and calculate the probability. And another good property of this function, were different from the previous step function, so unit step function, it is basically continuous on every area. So the function is differentiable at any point. And this differentiability is important in machine learning. Because, well, that means we can mathematically optimize the function. That means we can mathematically learn the shape of right form of the function from the data. Maybe this implies that we can because this implies that we can learn the right shape of the function from data. And let's move on to probability density function. So again, we are going to have some special session on this topic. So there are a bunch of different density functions defined by many statisticians. But well, basically the idea of probability density function is a function that can be used to represent a sample space. And that means at any given point in the sample space, so sample domain, can be interpreted as providing some quantity that looks like, or that could be understood as a probability. So here comes an example. So where everybody heard of normal distribution or Gaussian distribution or 정규 분포. So the shape of the Gaussian distribution represented in this way. So it is 1 over sigma root 2 pi exponent 2 where e to the negative where mean and standard mean and variance. So basically, where I already told you, but mean is mu, here is the sample mean, and sigma represent the standard deviation. Sigma square is variance. And the shape of this function looks like this. So this bell-shaped curve is where something we call the Gaussian distribution or Gaussian probability space. So in this simple function, there are only two unknowns. This is one, this is the second. So pi is constant pi, and x is the, oh, sorry. So there are some additional unknowns, but they are not completely unknown. They are sort of summarizing the observation. So these are something called as a parameter. And there is only one unknown, that is x, and where this fx can be understood as y. So basically there is only one unknown on the right hand side, there is another unknown on the left hand side. And what this Gaussian distribution is saying, you have a bunch of data. What you need to capture the trend of the data is only capturing the sample mean and sample deviation, sample standard deviation. Then you can complete this piece of the function. So where depending on the value of mean, where you can centralize the shape of this bell curve. And depending on the shape of the standard deviation, you can control the width of this bell curve. So if your data is scattered around very widely, so sometimes you have 100, sometimes you have 1, sometimes 2, 99. Well, say this is your data, your distribution would be looks like quite wide. Well, if you have data points scattered around this relatively narrow area, so 50, 51, 9, 49, 55, 44, or something like this, then most of the data points are found in the central location, and your bell curve looks like this. So that's the idea behind of this function, and I'm going to discuss a lot more similar to this distribution in the later class. So today I'm just trying to carry the idea what is the probability density function. So the important point here is where based on the observation, you can get some summarizing parameter, and depending on this parameter, you can effectively summarize your data distribution. And the name suggests where this function is able to generate probability density. So once you have this function, that means once you have set mu and sigma, where after that, if you have an observation in terms of x, you can calculate some value, and this value represents the probability. So say this value was x prime. You can calculate the probability of x prime.